So remember in Algebra 2, we use sigma notation as a shorthand for finding the sum of a series of input values over an interval, generally starting at 1 and ending at some other number n. Let's do some quick vocabulary before we move on. The index of summation is what I refers to. So I is the index of summation. The ith term, a sub I, means the ith term in the sum, and the upper and lower bounds would be n would be an upper bound, and 1 would be the lower bound in this case. So let's go ahead and put this together as a sum that we can look at just to remind ourselves how they're used. Let's find the sum of I values, input values, beginning at 1 and ending at 4 for 2I. Well, this notation tells us that first we're going to plug in 1 for I, so we get 2 times 1, and then summation means add. Next, we're going to plug in the next integer up. These are always integers. I values are integer increments. So this would be 2 times 2 plus the next integer up, 2 times 3 plus 2 times 4, and the upper bound tells us to stop at 4. Notice, though, before I go ahead and simplify and find the value, that each of these terms includes 2. So I could factor out a 2 and then add 1 plus 2 plus 3 plus 4. That's one way to look at it. Or I could have done that here. I could notice that when there's a constant, I could rewrite the sum with the constant value outside and then only use the summation to find the inside the parentheses, right? So that would be 1 plus 2. The next increment would be plus 3 plus 4. And you can see that that's exactly what I ended up with here. So whenever there's a constant in the ith term notation or the function notation, I can always pull the constant out and evaluate the simpler sum first. So now completing this problem, I would have 2 times 1 plus 2 is 3 plus 3 is 6 plus 4 is 10. And so this would be 20. Let's do another example, another shortcut that we can use. Suppose I'm given the sum I equals 1, and we're going to stop at 5 this time. And I have some polynomial, say 2I plus 3. Okay, again, this just tells me to plug in an integer, and increasing by 1 integer at each iteration or on each new term to add. So my first term would be 2 times 1 plus 3. This is going to get a little bit ugly for a second, but I need to make a point. And the second one would be 2 times 2 plus 3. The third one would be 2 times 3 plus 3, then 2 times 4 plus 3, and then 2 times 5 plus 3. All right, so if I look at this, I can see that the first term for each ith term looks a lot like this first rule I used, where I could pull out the 2 out in front and then evaluate it. But I can't pull out the 2 right in the beginning, because if I were to pull a 2 out and then evaluate I equals 1 to 5 of I plus 3, then really what I end up doing when I put it all together is I end up distributing a 2 back into both terms, and this one should not be multiplied by 2. So I can't do that. But I can notice that, excuse me, For the iterations 1 to 5, my plus 3, I have a 1 3, 2 threes, 3 threes, 4 threes, 5 threes. So my threes actually happen every single iteration, as do the 2 times 1, 2 times 2, and 2 times 3. So really, in this case, I can rewrite this as two separate sums. I could write the sum I equals 1 to 5 of 2I plus the sum of I equals 1 to 5 of 3. That is totally doable, and that will give me the same answer in a shortcut. So let's go ahead and do that. Well, the first one, I already know I can take a 2 out front and evaluate the sum I equals 1 to 5, and then add to that the sum from I goes from 1 to 5 of 3. Whoa, I did something wrong here. There we go, fixed it. All right, so first, let's do the 2 times 1 plus 2 plus 3 plus 4 plus 5, right? That's just this rule right here, not a problem there. And then I'm going to add to that the second sum, which basically says when I equals 1, the function equals 3. Plus, when I equals 2, oh, the function is still 3. Plus, when I equals 3, oh, the function is still 3, all the way until I get to I equals 5, which makes me stop. And that's exactly what I alluded to before. I have a 3 plus 3 plus 3 plus 3 plus 3. I have 5 of them, 1, 2, 3, 4, 5. So I ended up in the same place. Now if I finish this out, I get 2 times 9, 10, 15 plus, well, 3 times 5 is 15. So 2 times 15 plus 1 times 15 is 3 times 15, which equals 45. So this is a quick review of summation notation and kind of playing with a few of the shorthand tricks that we're allowed to use. There are others which you'll encounter or might need to look up to refresh your memory, but they're all available to you just as they were in Algebra 2. But we do want to look at a few particular sums that we'll be using in second semester calculus. So let's have a look at those real quick. So the first one applies a formula to the sum for the sum of integers from 1 to n of some constant value, and that's actually this one here. And what did I do when I got to the end? I noticed I could multiply 3 times 5, right? So there's a formula for this, and it's just c times n, which is what I showed you here. Another formula is for the sum of consecutive integers, I equals 1 to n of I. That means I'm going to take 1 and then add to that 2 and add to that 3 and add to that 4. I just keep making integer values. This is the famous Gauss the Butthead story. Gauss the Butthead being so called because while he was an amazing and important mathematician, he was definitely a butthead as a human. So his formula, famously told that his 4th grade or kindergarten, some young grade teacher wanted to keep him occupied and out of her way, and so sent him to add the first 100 integers together to find out what the value was. He found the answer within just a couple of minutes, and the reason is he discovered this formula when he was very, very young. So that's pretty impressive, even though he grew up to be a bit of an ass. All right, number 3, I equals 1. I guess if you're as brilliant as him, you can be an ass, so maybe I shouldn't say it like it's so judgmental. It might just be an okay process of being that brilliant. This formula is not very easy to memorize. The first two you should obviously commit to memory. These next two, not necessarily, but you should know that they exist so you can reference them. So this third one says that if I want to add consecutive I squared terms, perfect squares, so 1 squared, 2 squared, 3 squared, 4 squared, and on, this formula will give you your total sum so you don't have to do each term and then add them together. And last but not least, number 4 Similar to 3, only this time it's consecutive cubes. So the sum is I values start at 1 and end at n of i's cubed. This would be n squared times n plus 1 squared all over 4. Okay, so 4 formulas. 2 you should commit to memory. 2 you should remember exist so you can reference them whenever you need them. Have them in a place where you can look it up pretty quickly. The second 2 I would definitely give you if I gave them to you on a test. The first 2 I may or may not expect you to know it off the top of your head. All right, so let's use a couple of these to do an example. Let's evaluate the sum as I values start at 1 and end at 10 of some constant value, not some constant value, let's actually give it a constant, 5 plus I squared. Okay, so first let's use an earlier rule that we applied, which is let's break this into 2 separate sums. So you have the sum I goes 1 to 10 of 5 plus the sum I goes 1 to 10 of I squared. So if I had to do this longhand, I would have to write 5 plus 5 plus 5 plus 5 plus 5 all the way up to 10, and then 1 plus, oh gosh, can I do this in my head? 1 plus 4 plus 9 plus 16 all the way up to 10 perfect squares, or I can use the formula. Now that I've broken these out into 2 forms, I can say, well, 5 times 10 is my first sum, and then I'm going to add to that my second sum, which is 10 times this one, this one, 10 times 11 times 2 times 10 is 20 plus 1 is 21, all divided by 6. Let's get rid of whatever we can. I can get rid of a 3 here, leaving me with a 7 and a 2, and I can get rid of the 2, leaving me with a 5. All right, so 5 times 10 is 50, and then my denominator's gone. 5 times 7 is, I don't know if there's an easier way to do this. I'm going to have to scratch work it. So 5 times 7 is 35 times 11. So that's 5 and a 3, 3 and a 5, 5, 8, 3. 385 plus 50 should be 435. So you might be asking yourself, why on earth are we now doing sums when just yesterday we were doing antiderivatives? And the reason for that is that the integral is a very powerful tool for finding the area of an object. And we're used to working to find area, right? Base times height would be the area of a rectangle, or 1/2 base times height would be the area of a triangle. But what do you do if you have something that looks like that, and you want to find the area in this interval, this region here? This starts to get really tough. But finding this area directly, at this point in the game, we don't really have a way to do it, but we could estimate this area and then add to that the estimate of this area, and all we have to do is estimate this part up here, right, because we're dealing with a rectangle with a funny side. This, we could estimate the area, estimate the area, estimate the area. So if we could estimate the areas closely enough by taking small enough slices through the object, we can add all of those up, or sum them. We can add them up between 1 and 2 and 3 and 4 and 5 and 6 and so on to n. We could take all those little slices from 1 to n and add their sums up. Now, we don't have a function here to put in yet. That's part of what calculus is all about, is finding how to do that. But in the meantime, we can find closer and closer area values by taking smaller and smaller slices, as you can imagine. The estimated amount of this first section, if I take 2 sections, now I have a closer estimation twice. So 2 smaller estimations are closer to the actual area than one big estimation. I'll go over this a little bit more in our next lesson, but I wanted to give you a little heads up where you were going, and I had time on the video to do it. So that's why we're looking at sums and why we care about being able to evaluate sums.